All right, so, hi. I'm also going to speak in English. I think we would all be very confused if I tried to speak Spanish, myself included. So my apologies, but hopefully we can learn some interesting stuff about scriptable objects. So this talk is titled Scriptable Object Case Studies. My name is Matt Schell. I am a trainer on the R&D content team at Unity. Our department, we make a lot of the video tutorials and the demo projects. I also do a live training stream on Twitch every 2 weeks where we build a lot of projects and learn a lot of fun stuff. So I encourage you to check that out if that's something that you're interested in. And then those are also archived on YouTube a couple days after. I'm on Twitter, @MattMarafish. You can say hi. I'm on there all day long. So what is in this talk? So we are going to have a quick introduction to scriptable objects. First of all, who knows what a scriptable object is? Okay, cool. So I'm going to give a quick overview of scriptable objects, what they are. We're going to look at 2 use cases for scriptable objects. So one is a text adventure game, cutting-edge game format that you may have heard of. And the other is a pluggable AI system. So for building a finite state machine AI that we can change in the editor without changing the code. Hopefully we'll have a little time for Q&A at the end. And so let's begin. So what are scriptable objects? So scriptable objects are like mono behaviors, but they are not components. They're not attached to game objects, right? So most of the scripts that we're used to working with in Unity are always going to be attached to a game object with a transform and maybe some other components, maybe a renderer or rigid body or something. Scriptable objects are never attached to components, but they can be serialized and inspected, right? So we can set up a bunch of variables and edit them in the inspector. And perhaps most importantly, they can be stored as an asset. So this is one of the things that I really like about them. So we can make our own custom asset types that we can store in our project. So, is it very loud? It feels loud to me, but here is me talking very loudly. Here is me talking. Whoop. Hello. I am gone. I could probably just yell, but yeah, that's pretty much what you got. I'm a naturally a loud talker, so I apologize. I'll try to scream a little bit less. So why use scriptable objects? What are the problems that we can solve? So one is we can create custom. Maybe I'll move the mic a little further away from my mouth. Is that better? It's a little better. Okay. We can create custom asset types, like, for example, data tables, enemy statistics, right? Like the maximum hit points for an enemy or what items it might drop. We could store localization data, right? Tables of strings in order to localize our game or application. We can create pluggable objects that execute code. So we're going to see a couple examples of this where we can have an asset that actually has some functions inside it that we can plug in and have it. We can allow ourselves to modify the behavior of our game by plugging these things in, and we're going to look at that. Another cool thing about them is that they are assets and they do not reset when we're exiting play mode, right? So if you've ever had a scene playing, changed a property on a material, let's say change a material color, and then you exit play mode, you'll notice that the changes to the material will persist because it's an asset, right? It's not reset like scene objects when we exit play mode, and scriptable objects behave the same way. It also, on a performance level, we can speed up instantiation and save memory by moving data off of the prefab into the asset. So every time we instantiate something, we need to copy all of the data in its fields, and that's going to take up memory, right? So if we move a lot of those fields onto the scriptable object and just reference them, we can have one instance of that data in memory. So there's some performance benefit to be gained as well. Another thing that's really nice about it, I know one of my colleagues spoke a little bit earlier about the importance of using version control, source control, right? Please do this, please. We get a high degree of version control granularity and reduce scene and prefab editing conflicts. If you've ever worked in a team and you said, hey, are you editing the main level prefab, or are you editing this scene? Can you stop editing it so I can edit it? And done that whole really fun dance, right? You don't have to do that, because you can say, I'm just editing the data for the enemy, or I'm just editing this localization data from the UI, and I'm going to check that into my version control system and make a commit, and we can see what was edited. It was only that, not the scene, not the prefab, and so on. Some limitations. There are very few callbacks. So scriptable objects get on enable, on disable, and on destroy. And those are actually called when the object is loaded into memory, right? So it could be when the assemblies reload, or in a couple of other cases. And so they're not so useful for kind of hooking into the mono behavior callback ecosystem. So, but one way that you can overcome that is using proxy mono behaviors, right? So if you want something to happen on awake, you can just have a mono behavior that will then call whatever function you want in your scriptable object. Another thing, I wouldn't call this so much a limitation, but it's just something to get used to if you're used to using prefabs, is that there is a change in workflow, right? We are used to having the idea of, oh, I can take a prefab, drop it in the scene, and just change this one thing on this one prefab, and that instance is the only thing that's changed, right? Whereas if we make a change in a scriptable object that's being referenced throughout the project, it gets changed everywhere, right? It really is a global situation because it's an asset, right? So that's something to be mindful of, and just to get used to working that way. Yeah, as I said. So one of the patterns that we're going to look at today that kind of both of these projects are built around is the delegate pattern. So the idea of the delegate pattern is that the object, and so this is a software design pattern that you may have encountered elsewhere. It's also called the delegation pattern, same thing. So the idea here is that the object which handles the request uses a secondary object to complete the operation, passing in a reference to itself. So basically we have sort of helper objects, right? So let's say I have a power-up that's supposed to apply hit points to the player. Instead of the power-up containing all the code to do that, instead it will reference a helper object that applies the health, let's say, and so we'll have kind of two objects working together to accomplish the goal. This allows us to swap out one of the objects and have a kind of a little bit more flexible and extensible system. So in Unity, this allows us to create pluggable systems by assigning objects in the inspector. We're going to see that. It also, I think perhaps importantly, opens up opportunities for non-programmers to author content using building blocks created by programmers. So if you're a game designer or you're a member of a team where you're not as comfortable just diving into the code and editing the code, right, your programmer colleagues can build tools for you that will allow you to author content, including interactivity, without having to be a programmer and write code. So the first project we're going to look at is a text adventure game. The goal here is to create a flexible system for managing data and behavior in a text adventure game that's editable by non-coders, as I just said. The reason that I chose a text adventure game for this exercise is that, not that text adventure games are like the super hot new genre, right? Not since the 80s. But working with text allows us to focus on systems and workflow, not on content like artwork and animation and so on. So it's just a very stripped down example just to show the code and to show the workflow. So this game is built around a basic verb-noun grammar like examine, skull, go north, use orb, or whatever. So in it, we have several different types of scriptable objects. We have data assets, which include rooms that the player can enter into, and items which can be placed inside those rooms. We also have what I'm calling behavior assets, right? And these are assets which contain code that executes functions. In this category, we have input actions, right, which respond to the player. These are going to be things like go, use, examine, inventory. And then we have what are called action responses, which allow us to set up little custom behaviors within the system. So if the player does the right action for the puzzle, we'll open another door or whatever. So, demo time. So let's take a look at the Unity editor. Now I recognize this is, I'm going to try to zoom in on the appropriate stuff because it's going to be really hard to see, and I'll read the text to you. So here's our game. We're going to type Go Dungeon to begin. You head off to the dungeon. You're in a maze of twisty little passages all alike. You see a dark doorway to the north. A human skull lies in the corner. So we're going to say, a skull. We're going to examine skull. The skull appears blackened and charred. It smells of sulfur. Okay, that sounds nice. We're going to take the skull. You take the skull. Then we can look in our inventory. You look in your backpack. Inside you have skull, right? And it would show us a list of everything that we have. And worth noting that I didn't mention earlier, this project and the other one that I'm going to show, I have like a full 2-hour tutorial on writing the whole thing from scratch. So if you're curious about anything else separate from the scriptable objects, I will show some links at the end of the presentation where you can get access to that. So just so you know. Okay, so we've taken the skull. Okay, now let's try to go north. You are in a vast dark hall. There's a door to the south, heading back to the dungeon entrance. A glowing orb floats in midair. In the center of the room on a raised platform, there's a blackened, magic-scarred altar. We are going to examine the altar. There's a drawing of a skull scratched into the soot on the surface of the altar. Okay, let's try to use skull. Suddenly, there is a deep rumbling sound. Dust fills the air. The door back to the south slams shut. A secret passage is open to the west. And the glowing orb is still in midair, and so on. So we're going to go west. You enter the room. You see a set of stone steps leading to a wooden door, which is ajar. Light streams through the crack in the door. The secret door leads back to the east. So we're going to go steps. Hooray! You walk up the steps and open the door. You're blinded by the sun in your face. You have escaped the dungeon. You are free. And that is our game. The other thing that we can do is type gibberish. And it'll say, you attempted, blah, 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 but it doesn't seem like a good idea. Try to go somewhere or take, examine, or use something, right? So it's suggesting to us our appropriate verbs. Okay, so let's take a look at how this is actually put together. So let's look at the first type of scriptable object, which is a room, and we're going to look at the starting room. So let's try to make this bigger. How's that? Okay. So we have a field for the description, right? This is a string field with a text area attribute. I'll show the code in a moment. We have a room name, which is used in any puzzles. And then we have an array of exits. In this case, we only have one exit to the north, and we have a description of that exit. And then we have another field for a room, which is another scriptable object, which is the room that we'll move to if we use that exit. We also have an interactable object in the room, an item, which is the skull, right, that we saw. So let's take a quick look at the code for this. And this, I think I can just make the type bigger. Can you read it in the back? Bigger? It's a short script. Actually, I think that's as big as it goes. So there you go. All right, so the first thing we notice up here at the top is we're using the create asset menu attribute here. This is something that was fairly recently added and is one of the reasons I think when this didn't exist, you had to write a very small and relatively easy editor script to be able to create scriptable object assets. And I think for a long time, this is a reason people didn't use them because they didn't know about this and it felt like one step of friction. Now it's really easy to create them using the create asset menu attribute. So we have a public class that's a room. It inherits from scriptable object, right? This is all you need to do to use scriptable objects to make new ones is just have your class inherit from scriptable object instead of mono behavior, right? Which is the default when you create a new C# script. So we have the text area attribute. This just allows us to have a bigger text box. We have our description, our room name, our array of exits. And so the exits are maybe a little bit interesting. If we go to declaration, this is just a tiny serializable data class, right? This is not a mono behavior or a scriptable object. It's just a serializable C# class with a couple of fields in it. In this case, it would be north, south, east, or west, a description of the exit, and then the room that we want to change to, right, if we choose that exit. The reason, and you can actually see, if you can see that tiny inspector on the side there, the reason that I chose, let's zoom in and look, a serializable class is because it allows us to expand it in the inspector and edit its properties, right? So if we had another nested scriptable object, that would be more difficult, right? We would need like a custom editor. So we have our exits, and so then we can define how the player can move between rooms, right? We also have this skull, and let's take a look at that. So this is an interactable object. Let's zoom in. Maybe a little less. How's that? This is an interactable object, right? It has a noun, which is how we're going to address it. If we say use skull or examine skull, this is the string that we're going to need to type. We have the description, and then we also have another array of serializable classes called interactions, right? And this is kind of where, so the room class that we saw is just a pure data class, right? There's no interactivity involved there. It just allows us to display a description, display the exits, etc. Here, we're starting to get into some of the potentially interesting flexibility. So in the interactions, this skull has 3 possible interactions. It has the examine interaction, which is the simplest, take, and use. So examine is another scriptable object, right? So if we look here, we can see we have a folder of input actions, and we have in it the examine object. And let me zoom back out. And so here we can see the code for the examine script that allowed us to create that asset, right? So this is, again, we're using the create asset menu attribute, and then we're specifying a little custom menu, and that's going to cause it to appear here under assets, create, text adventure, and then in this case, we have responses, input actions, interactable objects, and rooms, right? So all we need to do is add that attribute to the top of the class to be able to create instances of it as an asset. This class examine inherits from input action, right? So input action, if we choose to go to declaration here, is a tiny abstract class, right? So this being an abstract class means that one of its functions, in this case, the respond to input function, has no implementation, right? So we're going to implement that only in the classes that inherit from it. And so what this allows us to do is to say, okay, I know anytime I want to respond to input, I'm going to be dealing with some kind of input action. I don't know how it's going to respond, and I don't need to know. Right? So it creates a layer of flexibility in our system so that we can then inherit from input action. So in the case of examine, all we're doing, so we have a public function that overrides respond to input, right? And it will then, in this case, it's just logging back the string from the description. It's just going to display the description string, right? So this is sort of our simplest input action in this case. Now, we also have the take action, input action, and take is a little bit more complex, right? And this is kind of where we start to see the pattern becoming more useful, because now we can say, okay, one input action does this very simple thing, but this one now, when we call respond to input, we're going to do a little bit more, right? We're going to check this dictionary to see if this item is in there, if it's allowed to be taken, and then we're going to log back a response. Finally, we have the use input action, and let's actually look at this in the inspector. So the use input action has no text response, but it has an action response, right? And you can see take up there has its action response is null, right? It has none. What the action response allows us to do is to plug in another type of object. In this case, it's an action response. It follows really the same pattern as the input actions. It's a little abstract class, and then we implement it. So in this case, we have, this is it's called a change room response, right? And really, this is just used so that we can create unique responses to certain puzzles, right? So if you bring the skull to the altar room and you use the skull, then this behavior is going to, this function is going to be called. But we could also additionally write, I only made one here because I was trying to keep this demo a little bit smaller, but we could also make one that kills the player, or that empties out their inventory, or turns them blind, or whatever we wanted to do that would be fun in our game. So this kind of creates another layer of flexibility where we just create new action responses and plug them into those slots, right? And theoretically, if we made a little set of these, if we had several of these, we could give this all to a game designer and say, okay, here's all your pieces. Here's your verbs. Here's a couple of action responses you can use to build puzzles. You can make as many items as you want, and you just type everything into fields and connect them in the inspector, and you don't actually have to engage with the code at all. Okay, so that is, and I apologize if I'm going a little bit fast here, but I'm sort of trying to cover a lot of stuff. And as I said earlier, if you want the 2.5-hour version of this, that's on YouTube, and I'll give you the link, where I go through and type all the text from scratch and explain everything in a lot more detail. This is like the 15-minute version. So that's exciting. Okay, so next, our pluggable AI system. Now, this uses really a similar pattern to achieve a very different outcome, right? So we're using this idea of pluggable objects and this delegate pattern, but in this case to drive a finite state machine-based AI that I have built on top of the existing tanks demo, which is available from the Unity Learn site, and there's also a long tutorial on that if you're curious. So the goal of the project, to create a modular system to control enemy behavior, which allows the authoring of new AI agent types, again, without additional scripting, right? So this allows us, and this is not just for game designers and non-programmers, right? I actually use this system in my own personal project where I have 20 different types of enemies, and it's really nice to be I want to make a new enemy type. I just go to my little set of pieces, combine them in a new way, and I have a new enemy type, and I don't have to write any new code. Or if I want to write one new unique behavior, I can do that without having to go into all my other scripts or create spaghetti. So in this case, we have one fairly insignificant data asset, which is the enemy stats asset, which just contains some data about the tanks, how far they can see and their hit points and move speed, I can't remember, but less the focus here. So the previous example has a lot more about storing data and using scriptable objects for data. This one is much more about behavior, right? So in this case, we have 3 behavior assets, and these are kind of all the core ingredients of creating a finite state machine, right? So we have states that our enemy can be in, right? Like patrolling or chasing. We have actions that the enemy can do within those states, like chasing or shooting. And then we have decisions which can cause the agent to change states, right? So for example, looking in front of themselves to see if they see the player or not, or scanning for a certain period of time to see if they've found the player. So more demo time. So here is our tanks project with the added content. And so I will just play it quickly so you can see. So we have 3 tanks. The blue tank is player controlled. The green tank is using our very simple chaser agent type. He's seen me, and he will now chase me until I'm dead. The red tank, you can see rotating, will look for the player, and then when it loses the player, or actually another tank, see he's trying to shoot the green tank now, will rotate and scan for, I think, 8 seconds. I'm going to die. See, he got his friend there. Take that. Ha ha. So the way this is set up is very similar conceptually. So we have, let's start at the state level, and let's start with our very simple chaser AI, right? The chaser AI has two states. It's either chasing or it's patrolling, right? So let's start in the patrol state, which is the state that it starts in. So if we highlight and let's zoom this in. So if we highlight, this thing is like on a slant, so it just slides back if I stop touching it. So we have, I can walk around, right? So we have here one action. So we have actions and we have transitions. And each of these are executed every update of the AI, right? So in this case, I'm updating them at the actual Unity update rate, so very often, right? But you could also update them at a slower rate if you wanted to save performance. So every update, this agent in this state is going to try to patrol, which just means moving between 3 waypoints, right? It's just going to walk in a triangle until it's time to change. It's also checking every update its transitions, and its transition that it has is this look decision, right? So it is going to look in front of it every frame using a sphere cast, right, which is like a wide ray cast. And if it detects another tank, right, either the player or the other agent, it is going to transition into a new state, right? So this is one state, the patrol state. And if it sees somebody, it's going to transition to the true state, right? So our look decision is going to return a Boolean value of true. It's going to say, okay, we saw somebody, we're going to go to the chase state. If we do not see anybody, we're going to remain in state, aka do nothing, right? We're just going to stay in this state until we actually see somebody. So we're just going to keep patrolling until we see somebody. So let's look at what happens when we go into the chase state. So in the chase state, we have 2 actions, right? And it's worth pointing out, let's look at what these actions look like. These are, let's just look at, for example, the chase target action. This is just another scriptable object asset which has it inherits from action, right? It overrides this act function. And if we look at action, it's almost exactly the same as our previous abstract class. So this is an abstract class that only has this one function, act, right? So anytime we have an action, we can just tell it to act. We don't need to know what it's going to do. We're just going to say, okay, do something, act, right? And then based on what is in the, where is that, chase target? Based on the way that act is implemented in the inheriting class, in this case, it's going to chase, right? And this is just using, actually, the nav mesh system to set the destination to the player and move towards them. So in this case, we are in the chaser state. Let's zoom back in. That's nice and big, right? There we go. So in this case, we're doing 2 actions every update, right? We have our chase action that we just saw, and then we also have an attack action, right? Which is we're going to raycast in front of, or sphere cast in front of the agent, look to see if there's somebody there, and if they are, shoot a bullet at them. And so one thing that's cool about this is just an array, right? So we could have it doing 40 different actions every update if we wanted to, or 0, as we're going to see in another state. So in this case, every frame it's going to try to chase, and it's going to try to attack. And then we also have an array of transitions, right? And again, just like in the other example, the transitions are just a serializable data class so that we can expand them and edit them in the inspector, and we just have an array of them as well. And so here we have and this AI actually is like a cheater. It doesn't play fair. Once it sees the player once, it will just pursue them till they're dead, right? Whether they hide or whatever, it doesn't matter. It just cheats, right? It knows magically where the player is, knows if they're alive, and will chase them forever, which is pretty unfair. But it's a video game, right? So it has an active state decision, right? Meaning it's going to check the active state of the player every update and say, is the player alive? If so, or is the target alive, right? Because it could be a player or an AI. Is the target alive? If so, I'm going to keep chasing. If the game object that is the target has been deactivated, which is how units die in this game, they just get turned off, then, okay, they've died, and now I'm going to return to the patrol state, right? So if the target is alive, we're going to remain in this state and keep chasing. And if they are dead, we are going to go back to patrolling, right? This is just a visualization color that I put in to draw some little gizmos in the scene view so you can see kind of what they're thinking, right? And so if they're in the chase state, it's going to be pink. And so that is like a very simple little state machine, right? We have two states. We look for the player. If we see them, we chase them until they're dead, and then we go back to patrolling, right? What's cool about this system is that we can create relatively easily additional agent types using most of the same tools. So if we look now at the scanner agent type, right? So the scanner is basically its states are in this folder, right? So we have now, we have our chase state and our patrol state, just like we had for our chaser AI, but we also have an alert state. So we have a third state now that we're adding to our kind of graph. So this is Mike's computer, so I'm not like totally used to it, so excuse my bumbling around. So if we look at the chase, if we look at the scanner patrol state, right, we can see that it's largely the same, right? He's going to patrol, he's going to look. If look returns true, he's going to chase. But importantly, he's not going to transition to the state object of the other AI. He's going to transition to his own chase state because it's going to be different, right? So if we go to the chase scanner state, we are going to see I'm doing on time. Doing good. All right. We're going to see that in addition to the usual chasing and attacking behavior, right, we also have a look decision, right? So this AI is more fair, right? It cheats less. In fact, it doesn't cheat at all, right? It's going to look every frame to see if it should continue pursuing the player, right? And so this is, and we're just reusing the same look decision, the same scriptable object as we were in the previous example. So it's going to look, and if it sees the player, it will keep chasing. But if the player gets behind a wall or somehow goes out of sight, it will switch to not go back to patrolling. It will go to a third state, which is our alert scanner state. And this is the state that you saw when the tank lost the player and was rotating, right, looking for the player. This is the state that it was in, right? So in this case, what we're going to be doing is there are no actions in this state, right? It's only decisions, right? Because it's standing still, it's not moving, it's just rotating, right? And so what we've done is we've made a new decision, which is a scan decision, and the true value for this, it will return true after it has scanned and turned around for a specified number of seconds. In this case, it's 8 seconds, right? So it will just scan for 8 seconds, and then if after 8 seconds it has scanned and not been interrupted, aka not seen anybody else, it's going to go back to the patrol state, right? So this has another step. It loses the player, scans around to look for them, and then returns to the patrol state. Now, it's also simultaneously looking, right? So every update in this state, it's using the same look decision that we used before to cast forward in front of itself and look to see if it can see anybody to chase after. If it does, it's going to transition to the chase state, right? They're going to become the target, and it's going to chase after them while looking at them, and otherwise it's going to remain in this state, effectively waiting for the scan decision to become true, meaning we finished circling and looking around. Just for kind of completeness sake, I will show you the enemy stats object. This is the only data scriptable object in here. We just have move speed, look range, look sphere cast radius, attack range, attack rate, etc. Just basic kind of table of statistics for each enemy. And in this case, they both share the same. They all have all the same values. So that is it. So I will point you to these links. You can take a picture of this page if you want. You can also find this stuff pretty easily on Google. The Text Adventure Live Training Archive is like a multi-part YouTube series of me walking through the whole Text Adventure piece and talking about the concepts behind it. And then the Pluggable AI Live Training Archive is the same thing. It's like a 10-part video series over an hour and a half where I actually write all the code and talk about it. So I know this was just kind of a shallow skimming of the surface, but I hope it was useful and informative. I will also strongly direct your attention to this talk by my colleague at Unity, Richard Fine. This is the person I stole all my ideas from. He's really smart, and this he's a really smart man with a really dumb name for his talk, Overthrowing the Monobehavior Tyranny in a Glorious Scriptable Object Revolution. So it's a little bit provocative, right? But it's a great, great talk, and a bunch of the ideas for this came from that, and I kind of took them and built them out and did my own thing with them. But it's and he gives kind of an hour-long deep discussion of scriptable objects, and you can learn a lot from it, so I recommend that you check that out. And thanks. That is the show for today. Thank you all. Thank you so much. I love Mexico City. I love being here, and I'm very honored to be here with you all. So thanks again.